All right, so now after spending some time viewing and watching my complete lecture on the sampling distribution of a population proportion, then let's now look at an actual example. And so here in this video lesson here, allow me to start out with example 1 right here. All right, so let's spend some time reading the wording description of the example 1 here. So from what we have here as the very beginning of at the very beginning of this problem, everything is described in a short sentence as following. Business major is known to be 30%. So this is something that should catch our attention, but I will get back to that later. So once again, business major is known to be 30% in the college students population. Sorry a little bit for the typo here, but it should be college students, plural. So, and that's everything about a population. So what we're looking at here is a population of college students, and what we know already is that in this population we found, and how is this value found? That's not the main concern of our problem here. So just somehow somebody already gave us this 30% as being a proportion of this, the proportion of business major in the college student population. And so now, before I get into part A of the example, where we start doing some problem here, allow me to bring up a couple understanding. So right here from this beginning description, what we have is a population. The population of college students, as I was saying earlier. And so what I see here is we're studying in this particular example 1 as a study. We are looking at business major being a category in our college students population. So in that way, now I'm switching over to my writing board here, and the college students population, let's consider that as the beginning population. Okay. So this is the college students population is considered as the beginning population. It's so using the term beginning population once again, in case as you have seen throughout some of my other video lessons, then this is a term that I tend to use on my own personal choice to indicate that this is the population where we're going to start picking samples from. Okay, so, and this college students population is not restricted to any particular school, and not even the schools in the United States. It could be all the schools, the universities worldwide as well. So college students population. And so from this, the understanding now is that from this beginning population, we are studying about a category. We're studying, or we're looking at this category being the business major. All right, and so that's our main category right here. So what matters now for us in our study is that among the college students here, whoever is in this business major, there are so many different fields in a business major, but as long as you are a business major, let's keep it simple that way. So as long as you are a business major, you're in this category, you're under that category. And so what only matters in this current study is that whether a student can be considered as being in the category, the business major category, or outside of the business major category. And so in that way, the value 30% that we have found in our understanding at this point now is considered as the population proportion. And this is the reason why I indicate that as a lowercase letter p. And so this is a population proportion. Okay, so that's just to understand. And then for this is the way how a population proportion is written in a traditional style, but when we actually get into doing the calculation work later on, a lot of times we will write that as a 0.3. And so again, just briefly, the whole reason that we come to a population proportion, because in this population we are studying about the category being business major. So we have found, or somebody told us, or somebody has given us that the proportion, the population proportion reflecting this category in our population is a 30%. And I made it clear earlier, I addressed this earlier, that nobody learning from this lesson needs to worry about how this value came from. Okay, we just take that as given information. And so it is something to be highlighted. And that's everything, really, everything we know about the beginning population. And so now, after looking at some information regarding the beginning population, let's look further into the wording description. So now we're starting to get into part A of the example. So part A here, right from the beginning, it says, in a sample of 40 college students. The question of this example, the question of this part A is asking, in this sample of 40 college students, what is the probability that less than 16, so 16 of the college students in this sample, so what is the probability that less than 16 is in business major? So you can already understand based on the wording that among these 40 college students that we picked as a sample, then some of them are in the business major and some of them are not. Some of them is in the category and some of them are not. And so in that way, what I see here is that we picked a sample of 40 college students from this beginning population. And so right here with this number, and I'm going to re-highlight this, right here at that number, this is our sample size. So now I am going to write it down that we have a given, we know, and a lot of times sample size is on our own choice. We decided our own sample size, as you have already learned through the video lessons, lesson about sampling distributions. And so sample size here, since we chose, we are the one that collects sample, we should always know our sample size. So here our sample size being 40 college students. So once again, now it's becoming even more clear that the reason why I've always been, in my teaching experience, I've always been telling my students that the population here is regarded as the beginning population, simply because from this population we pick samples. So in our sample here, we have decided to pick 40 students. So you got to realize that this is not the only sample. So now let me draw a quick sketch here. Maybe this is our sample, 40 students. And then this is some part of the scratch work right here. So allow me to keep it in a separate space out here. So in our sample here, we may or we may not find about just 5 students who fall into this category, being the business major. And then, now as I have made it clear, this is just a sample size. That means if we picked 40 students, somebody else can pick another sample of 40 students, 40 college students from the same population. And so maybe that other sample may come out as a count 6 students being in the business major category. And then some other samples may show some unlucky sample may show 0 count. And then some other sample may show 15 out of 40. So all samples, in our understanding at this point, all samples should be with the same sample size, 40. So just the description of one sample here kind of tells us the description of the entire family of all other samples out there. And then somebody may pick a sample where in 40 students, 40 college students, the count for business major being 16. And then there are even more. So some other sample being so lucky that in 40 college students, the sample may count up to 39 college students, 39 business major. And even more lucky samples, 40 out of 40. So these are all the different possible counts that may happen in a sample or in any sample of 40 college students. Now, don't get me wrong in one way, that each one of these values may also have repeats. We may find 5 college students in our sample having being in the business major, but somebody else also may run into the same count with us as well. So here I'm purposely just listing all the individual counts, but keep in mind that any one of these counts right here may be repeated. So now applying our understanding about the sampling distribution of a proportion. We are studying about the business major proportion. So this is the sampling distribution, or this is a sampling distribution of that proportion, being the business major among the college students population. And so this is the reason why for this particular problem, and applying our understanding from the general understanding of sampling distribution of a proportion, I regard to this population. So this, what we realize now is that we have a population of sample proportions. Any of these values is a p hat. This is a p hat. This is another value of a p hat. This is another value of a p hat. Sample proportion value, a sample proportion value. And we have so many, and up to the point that infinitely many sample proportions values that happen here. So any of these value is regarded generally as a random variable, capital P hat. And I had thorough explanation in my general lecture about what a sampling distribution of a proportion is. So the sample size is 40, so here I'm using capital P hat 40. And what it means here is that any value here is the proportion of a business major. So in any of these sample, we also look for the proportion of a business major, but not all of them is going to agree with 30. So 30 here is already known and agreed to be the population proportion, but these are samples and different sample values. So they may or they may not agree with the actual population proportion value. So now generally speaking, again, P hat here represents, or any value of the P hat, capital 40 is the proportion of business major. In a sample of 40 college students. All right, so now this is a population of sample proportion values. Or we can write that formal definition here. P hat 40 is the proportion in a sample of 40 college students. All right. And so now at this point, upon successfully defining the random variable that represents any of our sample proportion value here, and at this point we are ready to do the following. Let's now formulate the question. Formulate the symbolic question right here. So back on the wording description of the problem. So now when we get into the actual question, in a sample of college students, what is the probability that less than 16 is in business major? So now on my writing board here, after I have listed down all of these possible counts that can happen. So some sample, again, as I described earlier, some sample may run into 0 count for business major. Some other sample may run into 5 college students being in a business major. some lucky sample, extremely lucky sample, may run into 40 out of 40. So these are the count of business major in any particular sample of 40 college students. And this is the reason why we have the kind of problem as following. We formulate the problem as following. The question in our part A is asking, what is the probability? So in traditional probability symbolic term right here, P in parentheses, we want to find out, hey, among all of these possible sample proportion values, what's the chance that we can find a sample proportion value, capital P hat 40, being less than 16? Being less than 16. And that's what it said in the worded description of the problem. What is the probability that less than 16 is in, and so here apparently it's less than 16 of the college students in this sample over here is in business major. And so in that way, to be even more precise, 16 here is 16 out of 40 students, because as it said earlier, in 40 college students, we want less than 16. So what's the chance, basically as an overall picture of the problem, we want to find out what's the chance we run into any one of these sample from here to anywhere lower in the count. So I put brackets around these values that we want to consider. Indeed, as a matter of fact, to be precise, we only want to be anywhere from 15 or less, because we want less than 16 over 40. And as a quick calculation, 16 over 40 in decimals is a 0.4. So back in the wording, back in the writing of our problem right here, as we're now at this point, we're still formulating the symbolic statement of our question right here. So this probability, this symbolic probability question is the same as saying we want to find the probability that our capital P hat 40 as a value being less than 0.4. And that's what we saw on the calculator screen earlier. And so now, in order to get started into answering the problem here, let's look at the following. So I discussed in the general lecture about a sampling distribution of a proportion. Our proportion that we're particularly looking at is the business major. So this is a sampling distribution of this proportion. But now we've learned from the general lecture that since these are all data values, so this is a data value, represent any one of these data values here represents a sample proportion. So, and what we have here is a population of sample proportion values. So in that way, as long as we have a population of data values, we can find the mean. And this is a population, so it makes sense to use mu right here, the population mean of all sample proportion. So I gave a detailed explanation about what a mu p hat is back in my general lecture about the sampling distribution of a proportion. So this is what we need to know this value right here. We need to know this average, this center of all sample proportion values in this population here. So now this is what we need to know right here. This average, instead of brutally doing the math, instead of going through adding up all of the sample proportion values and divide by how many there are existing out there, which seems like a very hard work waiting ahead for us, there is a theorem that for our class it is not required to know precisely where that theorem comes from and how it's proven, but we can use directly the results from that theorem. The theorem is stating that we can bypass averaging out all of these sample proportion values, but because by doing that, it will just come down being equal to P. So my point now is that there is a theorem that guarantees this result, mu P hat, which is the average of all these sample proportion values, but turns out after the calculation turns out equal exact value with P. So what is the good impact of this? And make note again, I emphasize this in my general lecture that mu p hat, or the mu value for any population, is regarded or is understood as the center of that population. So if we have what we have here, if what we have here is a population of data, then mu p hat is acting as the center of that population data. But as a further impact right here, our p value is previously given. So that means for this population, for this distribution of sample proportion values, we can quickly find out that the center equals precisely 0.3 as stated by this theorem. So again, I was saying earlier that for our class here that we're learning, the main aim of this particular lecture is for a class where we don't need to go that detailed about looking closely at the theorem. So here I'm just telling that information that this result is guaranteed by a theorem, and it was formally proven. And here, right from this result guaranteed by that theorem as said, then applying that into this problem, we will consequently have the center of our population here, the center of this population of sample proportions will equal exactly 0.3, and that is the consequence. And likewise, or similarly, any population, after recognizing the center of the population data, the next thing is to find average spread. And so average spread, or in a formal way of saying, this is the standard deviation, the population standard deviation. And that's the reason why I'm using sigma value right here. I'm considering this data here, this distribution of sample proportions here, as a population of sample proportions. So average spread, or population standard deviation of all sample proportions. The theorem that I said earlier also has a guarantee that calculating this average spread on this population proportion can be done as simple as, or as easily as, multiplying p, this value right here, with 1 minus p, and divided by n, which is namely our sample size indicated here. And now this quotient is going to inside a square root. So we take a final square root of the entire quotient here. And that is how we can easily calculate the average spread. This formula is for calculating the average spread. Average spread, or average spreading of our population or distribution of sample proportions. And so now with this formula that we've learned to calculate, to quickly and easily calculate the average spread on this population, then consequently, since we already knew our beginning population had that population proportion being 30% or 0.3, then consequently our sigma p hat for this population of sample proportions will equal to whichever that comes out from the following calculation. We're going to take the square root of 0.3, multiply with 1 minus 0.3 inside the square root, and divide it by capital N being 40 in this case. And so now I'm going to spend some time doing the calculation for this setup right here. All right, so on the calculator, to make it simple for anyone, I'm going to use the very basic command right here. So we have 0.3 times 1 minus 0.3, and we can divide all that by 40. And this gives us this value, but notice that this is the value before we take square root. So in the next step, I am going to take square root and of the previous answer. So I'm going to put 0.00525 inside the square root here. And anyone viewing the lesson here may know a better syntax to go around, but but I decided to go with this very basic in case anyone is not too familiar with all the different syntaxes of a calculator. So here I'll go second answer. All right, so this is now the final calculation for our average spread on this population of sample proportions. So I gotta make it clear again, and I have all those explanations back in my general lecture regarding the sampling distribution of a proportion, but this is a population, and that was also a population. These are two different populations. This is a beginning population, and this is a population we created by picking samples. Okay? And so now the average spread on this population is 0.0725. So now that we have a center of our population, and we also have average spread of this population. So now we are ready to find how much probability, or among all of these sample proportion values, what's our chance of getting a sample proportion value in a sample of 40 being less than 0.4 or being less than 16 as a count. So in order to do this, allow me to skip this change the steps around a little bit, and then once I've finished giving all the explanations, then I will set anyone learning from the lesson here into the formal procedural order of the steps right here. But let's pretend that if we put the entire population of data here on a bell curve, so, or we can say that assuming that our data here can be placed on a bell curve, our population of all sample proportion values can be placed on a bell curve. So left and right on this line right here is indicating low values to high values, low sample proportion values to high sample proportion values. But the center here is 0.3. As you have already learned up to this point, the way how a bell curve is. Center of the data is always exactly in the middle, and it's a bell curve shape. So any value that we can find on this line here is a sample proportion. So capital P hat 40 is what we generally regard here as the name of the random variable. And so in this case right here, and for the way how the bell curve here is, we currently know that average spread on this bell curve is calculated previously to be 0.0725. So in that way, now being 0.4 is somewhere to the right hand side. So we want our sample proportion value to fall below this, the threshold value right here. And so 0.4 on this bell curve is about somewhere to the right hand side of 0.3, the center of the bell curve. And so now you can start seeing how these informations are all connected together. We gotta find center so that we know where to place in the middle of our bell curve. And this center, this average spread right here is an indication of how largely spread it or how narrowly spread it our bell curve would be. We won't see a direct, we won't see directly how it changes shape right here, but in the way how you have learned previously about how we operate with bell curve, then we always note the standard deviation of a bell curve somewhere next to the bell curve here. And so from this data, from this value being 0.4, we want to look at the probability that our random variable falls below 0.4. So falling below 0.4 here is translated in, or is understood as a shaded area to the left hand side on the bell curve. Okay, and so that's how we're about to handle the problem right here. We think of this population here as a bell curve data. Okay, we imagine that this population here can be placed on a bell curve. So measuring this probability is the same as shading the area on this bell curve to the left hand side, because we want because the problem is indicating less than 0.4. And then we have to know the center so that we can know where to place and how to make our shading. And then we note our average spread somewhere on the bell curve. Okay, so just a couple reminders about how we apply our skills in operating or working with the bell curve into a problem like this. And so now once we've had the picture of the bell curve drawn right here and made the proper shading right here, then all the standard work comes out for all of the standard steps come out for working with the shaded area on the bell curve. From where our value stands right here, we're going to do the following. So 0.4 minus 0.3, the center of the bell curve, and we're dividing that by this average spread that was calculated here. So 0.4 minus 0.3, and that difference there divided by the standard deviation of our bell curve, 0.0725. This is our work of finding the z-score. So this is getting us the z-score of our value 0.4 on this bell curve. And this is my style of teaching and my stat students, even though in these modern days there are technologies that directly get you the area here on this bell curve, but I want my students to maintain, I always want to give this reminder that I want my students to maintain the understanding of having a z-score right here, because somewhere here and there you will see z-score will impact your understanding. So here, instead of directly rushing into allowing calculator to solve the problem for you or to find the area for you, I want you to first get the z-score of this problem right here, of this value 0.4. So on the calculator, to find our z-score, 0.4 minus 0.3, and I'm dividing that by 0.0725. And now our z-score here, for anyone who has learned with me up to this point right here, then throughout all of my lectures, I use 2 decimal places for z-scores. However, if you're working on your own problem, make sure you watch for rounding requirements. So with this lengthy calculated z-score, I'm going to write on my board here, I'm going to conclude my z-score that we're using here as being 1.38. So now upon knowing the z-score for our problem here, finding the area, or symbolically as a statement, finding the probability where our p hat 40 being less than 0.4, this probability is the same as the probability on the standard normal distribution curve that we're looking at, the z-score being less than 1.38. And that's what I'm pointing out to right here. So 1.38. And now we're going to start letting calculator that can handle this calculation for us. So in my style, again, in my style of teaching stats right here, I want to have my students to retain the skill of using z-score. So now it's just a matter of running the normal CDF command right here. So using the TI calculator is just my choice for this lecture, but outside of the TI calculator, there are other calculators that can handle the similar functionality right here. So with this advanced TI-84 plus CE calculator, this is how I can calculate the area to the left-hand side, shaded to the left-hand side of z-score 1.38. We go second distribution, and option number 2 right here, normal CDF. And I'm going to click enter. In case you have a TI-83 or an older 84 calculator, then after selecting the normal CDF command as you have seen earlier, instead of seeing the menu like earlier, you will see the actual command being printed directly here. Now let's get back to the one I was using earlier. And so just like how I have already explained when we were still working with the standard normal distribution, then anytime we're calculating area on a bell curve here. At least for students who are studying directly with me, I always want to default mu on the bell curve to 0 and sigma 1. And now our area is shaded infinitely to the left-hand side. So low end is a negative 1E99. Or if anyone is new to this lesson, we can go negative 1. The EE button is here, right above the comma key, negative 1E99. That's a way to indicate an infinite lower end of the area on this bell curve that we're currently working with. And the upper value here is where we enter the z-score that we found previously on the writing board, 1.38. All right. For a TI-83 or an older TI-84 calculator. So the first number to enter here after the parentheses here is the negative 1E99. But then we need to put a comma. And then the upper end is the next number after the comma, 1.38. And then we put another comma, and then 0 is for mu, and another comma, and 1 is for the standard deviation, and we close the parentheses. So this is how anyone using a TI calculator that's older than somehow older than and it shows you a direct command instead of a menu, then this is how you can complete that command before getting the actual answer over here. All right, and so now back to this calculator here. I can just keep hitting enter a few more times, and now after finishing out, see, this is also exactly like the way how the older calculators we'll place these values right here. Low end, upper end, center, and average spread is here, and with the closing parentheses. And now we are ready to hit enter to come out with the final answer here. So this is the final probability, 0.9162, and supposedly a lot longer. And so completing out a normal CDF command, I can briefly write down negative 1 EE, but this is I'm assuming that anyone viewing the lesson with me here is using the similar TI calculator. But if in case you are using other calculators, there should be similar commands or functionality. 1.38, 0, 1. Okay, and now hitting enter, we will have the answer here throughout most of my lecture. I'm going to use 4 decimal places, so 0.9162. Unless in some special case that needs to be specified otherwise. And when you are doing your own problem right here, make sure you watch for the rounding requirements of the final probability right here. So, what is the meaning of this probability? To make it easier, sometimes you may want to put this as a percentage. So 0.9162 is equivalent to a final percentage being 91.62%. Okay. So what is the meaning what is the meaning of this final probability? It means that now anytime think about from this beginning population, the population of all college students. Anytime if we picked a sample of 40 students from this population, then the chance of having the count less than 16 in the business major is a high chance right here, quite high, 91.62% chance of time. Okay, so 91.62% of time we're gonna run into a sample of 40 college students where less than 16 of them are in the business major. All right, so now that we have found the answer to this particular problem here, and allow me now at this point to bring in one last piece of explanation. So we already knew earlier that we have come to the final answer in terms of how big that area here is on the bell curve, being as large as, in decimal, 4 decimal places, 0.9162. Or if we were thinking of that as a percentage, then that was about a 91.62%. And I gave the understanding in terms of the meaning of this final answer here. But now, if we look back into the steps here, there was one critical step that I decided not to bring in until now that we have found the final answer. So let's roll back to that step where I pointed out that the whole reason how we can come to this final answer is that we calculated this probability treating the data here, treating the population data here as a bell curve data. And that was the whole reason why we had to do z-score here by subtracting our 0.4 value on the bell curve with the center of the bell curve and divided by the standard deviation of this sampling distribution of the proportion. But now the big question that I was not able to answer earlier, and now it's time for me, and in case you didn't have that question in mind earlier, and now it's time that I need to point it out right here. But as a start understanding right here, how did I know, or how did we know? How did we know to use the bell curve to work with? All right, so that's the main concern right there. How did we know in the beginning, earlier when I was pointing that out, all I was doing is to tell anyone viewing the lesson that we were going to solve this problem as a bell curve problem, meaning I'm going to treat this population here of sample proportions as a normally distributed population, as a population that can be placed on a bell curve, and I said that earlier. But now, what important information that led us to decide using the bell curve to solve the problem? The reason there's this question here is simply because now, as you have seen from my earlier lecture, from my general lecture about the sampling distribution or any sampling distribution, and here particularly the sampling distribution for the proportion, then any distribution, any population of data will end up eventually with a distribution shape. But there could still be so many different distribution shapes out there. There could be a skewed right distribution shape. Sometimes our distribution can be a skewed left distribution shape, as already explained in the general lecture about sampling distribution. And furthermore, there could be some symmetric distribution shape, but not necessarily a bell curve. So that's why, how did we know in the beginning? How did we know before we get into the calculation here? The critical logical understanding here is that how did we know that our distribution shape for this population of sample proportions can be placed on a bell curve, or how did we verify that this distribution was a normally distributed data? And so, having that question in mind, that means before we can even put our data on the bell curve and start solving the problem here, there was a critical step that I did not show earlier. So the step was done as following, and this now is a real fact right here. This step I'm about to show here is a proven fact from the same theorem that stated about how we can find the mu p hat and the sigma p hat here. So in that same theorem guaranteeing the way how we can calculate these two values, that theorem there also stated that from the sample size that we are doing, being 40, from the sample size currently being 40 for each sample in our distribution, we can multiply with 0.3 And so take good note about the role of this 0.3. This 0.3 is the given population proportion. So now from where our sample size that we're working with, the sample size in our distribution, we just simply multiply with the known population proportion. That product here, this product here will give us a count, some kind of count. So 0.3 times 40 is going to be numerically as a count 12. And this count was above 10. And I want anyone learning from this lesson is to pay close attention to this. In a more advanced course, where anyone learning in that advanced course will get a chance to understand where this 10 come from, and to see in details explanations about the theorem I was stating. But so now I'm introducing a way to verify, a way to decide whether we can use the bell curve to solve the problem, to find this probability. And so as part of that method right here, right from the sample size that we were using, I multiply with the given population proportion. And that product there came out with a count being 12. And that count is to be compared directly with 10. And so this 10 right here, I put in red ink to indicate that for our level of learning here in this lesson, we just simply take that as a rule. So anytime that our sample size in each sample of the distribution here multiplied with the known given population proportion and come out with a count above 10, then we're halfway good to go. So now this is not the only requirement. So now in the next step, the same sample size that for each sample that we were doing, I am going to multiply with 1 minus 0.3. So 0.3 again is the currently known population proportion. The sample size in each of our sample here is also multiplied with 1 minus 0.3. So take a note here that 1 minus 0.3 is really 0.7. So in other words, as a math right here, 0.7 times 40, we will have another count. So we need to have two requirements here fulfilled. 40 times 0.3 to come out with a count. And now we want that count to be above 10. And obviously it did happen here. So now 40 times 0.7, we come out with a count being 28. So this count here is again greater than 10. And again, make that special note about this 10. So the reasoning here, the idea that I was showing here is that anytime in order to decide whether we can use the bell curve to solve our problem of this kind right here, that we take the sample size, multiply that with the known given population proportion, and also multiply the sample size with 1 minus the known population proportion. If, or let's put it this way, as long as the two requirements here are all coming out to be greater than or equal 10. And that's what I did here. The 12 that came out from 40 times 0.3 was above 10. So we passed the first requirement, one of the requirements here. And also we need to check with the next requirement. The sample size multiplied with 1 minus the known population proportion. It also needs to be above 10. So as long as we meet the two requirements here. So that's one requirement and this is another requirement. So that and that. As long as we meet both requirements here, then we can legally use the bell curve to solve this problem or to find the probability as required in the problem, like that. But then allow me to stop the explanation here. If anyone in case is having a question of how did that 10 come out from, that needs to wait to a more advanced course in statistics here. And how was this fact proven that was also, that should be introduced at a more advanced course in statistics here. But then back in the end, as far as the structural steps right here, this step where I verified the user of the bell curve should have been done right after I found the center and the average spread of the data. And then once we can verify that our sampling distribution here can be placed on a bell curve, then we can go ahead and treat the problem entirely as a bell curve. All right, and so before we completely done with this particular part A of the example and head out to another the part of this same example over here, then allow me to point out the generality of this problem we just went through right here. So basically what we have here is that from any beginning population, where we study about a proportion that reflects a category, then we pick a sample, and that sample represents an entire distribution of sample proportions. And I use the subscript capital N over here to represent the sample size, or the size in each sample. So this capital P hat sub n, just like the idea we have learned in our understanding in our general lecture about the sampling distribution of a proportion, then this represents the sample, the proportion of the category. Okay, whatever category that was that we're studying. So the proportion of the category in a sample of size n. And from this understanding that, and from this realization that we're having an entire population of sample proportion here, then we basically want to find, for this kind of problem particularly, we want to find the chance, the probability, because here in this distribution there are many sample proportions like that can happen. Our sample being described in the problem is only one among the infinitely many other samples. So now we want to find the chance that anytime we pick up a sample in that description, then what's the chance that our sample or sample proportion value is in an interval value. That's the whole idea right there. So in this particular problem, part A, we were doing specifically find the probability where our sample proportion of size 40 right here is being below 0.4. See? So below 0.4 here means anywhere less than 0.4. This is an interval of values. That's what it is generally. Okay, and so as part of the way to solve the problem, then we first need to find the center mu p hat symbolically of this sampling distribution, and then the next step is to find the average spread of this distribution, and further we need to verify whether our random variable capital P hat with subscript n can be placed or not on a bell curve. And so this symbol, if we recall from our understanding regarding a normal distribution, this symbol means whether can we, or is this sampling distribution normally distributed with center mu p hat and sigma average spread sigma p hat. So we need to verify that, and then we're going to start using z-score and then run our normal CDF command.